Welcome to this session of Engineering Trainer TV. My name is Luc Hennen. I'm the CEO of EngineeringTrainer.com. And today we will have a conversation with Johannes Homan. Johannes is a fatigue and damage tolerance specialist and trainer, and also works as an independent consultant in his daily life. We'll be discussing the topic of fatigue analysis, a specific example in which we will discuss the approach that a fatigue specialist might use versus the approach that an FEA engineer might use, and a typical pitfall in this matter. First of all, Johannes, it's great to have you on board. How are you doing today?
I'm fine, Luc. Thank you for having me in this interview. And looking forward to it to discuss this nice topic.
Nice. Looking forward to it as well. Now, I do anticipate quite a technical conversation. So to anybody watching, hopefully this is interesting to you, especially if you're involved in fatigue assessment and finite element analysis. Now, let me take share my screen, just to highlight the fact that this conversation is very closely related to the training courses on fatigue that Johannes provides on EngineeringTrainer.com. He provides on-demand courses, virtual instructor-led training, and can also be booked for in-company deep dive courses. So make sure to head over to EngineeringTrainer.com to check out those, and obviously also subscribe to the Engineering Trainer YouTube channel and LinkedIn channels if you want to stay up to date. Now, the course I have in front of me that I'm sharing in my screen, as you can see, is the comprehensive guide to fatigue that Johannes set up, which is an on-demand course with 14 modules and is quite substantial and a real deep dive when it comes to understanding fatigue in materials. Having said this, let's head over to the topic of today, and I'll switch the scene such that you can share your screen, Johannes. Give me 1 second. All right. So, Johannes, currently your screen is being shared. And I invite you to introduce the topic and let's get started.
Well, before I start with the example of this calculation, I will tell you a little bit about how an SN curve is defined. An SN curve is a representation of number of cycles to failure, and then depending on the applied stress amplitude. So in this diagram, what you see are two curves, one for, let's say, unnotched material, so basically some kind of a small bar or whatever, which is tested, and another curve, the orange one, with a notch, and the notch causes an inhomogeneous stress distribution in your structure, leading to some stress peak at a location, and that's then the critical location. For such a situation, the SN curve will be somewhat lower, as you can see in the diagram, especially at large number of cycles to failure. On the other hand, when you look at stress levels close to the tensile strength of the material, you will see that those curves are more or less the same.
Sorry to jump in, Johannes.
Yeah.
Just for my understanding, how is the fatigue limit at for the orange one? So KT is 2.5. So the one with the notch.
Yeah.
How is that typically determined?
Well, the KT 2.5, that's the KT, that's the stress concentration factor. So that's basically the stress level at the notch, the maximum stress level, divided by the nominal stress in the net section. So basically it defines your stress level at the notch. And the fatigue limit is roughly that factor KT lower than the fatigue limit for the case you don't have a notch. So as you can see on the bottom right, limit for KT 2.5 is approximately limit KT is 1 divided by that KT 2.5. As I said, it's approximately, in reality, it's often somewhat higher, but for a first approach, it's a good approach.
All right, it's a bit hard to see due to the log scale, but it's definitely true. Another question about this. So, I mean, we're looking at the stress limits versus the number of cycles,
Yes.
or at a certain number of cycles. At the upper stress limit, so at low number of cycles, so on the left of the curve, the stress level is well above the yield strength. How is that typically handled in this SN curve?
Basically, in reality, you won't use that part of the SN curve because, as you mentioned, it's already above the yield limit, so it's plastic deformation you will get. And when you look at high cycle fatigue, which topic we are discussing now, we mainly look to elastic behavior. So it's for modeling of the curve used, but for practical use, you can neglect that part. It's nice to see that on the left side of the SN curves, there's no real difference between KT1 and KT2.5. For that reason, it's nice to show.
All right, thanks. Yeah.
Okay, shall we go to the next slide and define our test case problem? What we will do is basically analyze this very simple geometry component. It's a strip with a hole in it, and this hole creates a stress peak at the edge of the hole, 2.5 times larger than the nominal stress, and the nominal stress is the stress in the net section. The loading we apply is, it's a cyclic loading with a mean stress level of 90 MPa and also an amplitude of 90 MPa, megapascal, giving a maximum stress level of 180 MPa, a minimum of 0 MPa, and we call that an R equals 0 loading. R is in this case the ratio between the minimum and the maximum stress level within the cycle. And since the minimum stress level is 0, we call it R is 0.
Just to jump in again, like the value 2.5, or in other words, the KT value is geometry specific, right?
Yes, it depends on the geometry. For example, if the strip is much wider with the same diameter of the hole, the KT will be a bit larger, but also the shape of the hole. In this case, it's circular, but if it's elliptical, then it might change as well.
Yeah.
And to be clear, we are talking about the applied stress level and loading. Those are nominal stresses.
Right. Yeah. And how do you typically know KT, Johannes?
You could find it in handbooks. In the past, there have been many analytical analysis made to derive such a KT value, but nowadays you can easily do that within a finite element calculation. If you have a let's say fine mesh, then you can calculate quite well what the peak stresses are at the edge of the hole, and that way you define what the KT value is.
Yeah. All right. Thanks. Yeah.
Okay, we defined a test case problem. Shall we go to the next slide? Well, to do the analysis, to know what the fatigue life is, we need to have some SN curves. And in this specific example, we generated the SN curves by doing tests on exactly that same structure. So the same strip with the open hole. We used that to perform fatigue tests at different stress levels. And that gives us a SN curve for KT is 2.5. So different stress levels, but all with R equal 0. You could do the same for KT is 1, so without the hole, and then you would get the blue curve. So we have two curves, KT is 1 and KT is 2.5. well, you can make you can represent those curves with an equation for the sloped part. That's often done with the so-called Pascal equation. I think that one is on the next slide. Basically, it says the stress amplitude to the power k times the life to failure, so n, equals a constant. And that constant, well, you can derive by taking the transition point where it goes from the slope part to the fatigue limit part, so the horizontal part at, in this case, 10 to the power 6 cycles, so 1 million cycles. So that way you have your SN curve determined, and those curves are used as input for the analysis.
Yeah, and are they always known? For example, the KT value for 2.5 is test data for KT 2.5 or any other KT value typically available?
In the public domain, you mainly find data for KT1, so on unnotched specimens, KT is 2.5. Sometimes in company data is available, sometimes it's not. But if you need it, it can be derived from the KT1 data. First approximation would be then to take the fatigue limit for KT1 and divide it by 2.5, for example. And that would leave you or give you a certain fatigue limit for the KTS 2.5 curve. As you can see in the table, if we would do that, you would end up with a different value. 155 is the fatigue limit for KTS1 and 68 for 2.5. If you divide 155 by 2.5, you would probably get a bit different value, but the 68 MPa is then, in this case, the actual data derived from tests.
And the transition is the same 10 to the power of 6 for both? Is that always the case?
If you look to steel, then it's roughly always the case. It's for steel materials, it's often between 1 and 2 million cycles. So if you take the 1 million cycles, as in this case, then you would be somewhat conservative. Looking to some other materials, for example, aluminum, you would see that transition point can be at a different number of cycles. So it depends a bit on the material.
Yeah, but for one material, it's
for steel, this is an often used number, and steel is an often used material, of course, in construction.
Yeah. All right, thanks.
Yeah. Okay. Let's start with the analysis then, the way I would do it. So let's say the fatigue specialist approach. Basically we have the experimental data. We used this specimen, this strip with the open hole, to establish this SN curve for KT's 2.5. So basically what we do is, looking at the curve, we had a stress amplitude of 90, so we look here to 90 MPa and we read what the number of cycles to failure is. Well, the diagram is of course very hard to use to read an exact number, so we can also use this Pascal equation, and with some rewriting we find that the number of cycles equals 10 to the power 6, and then we have that k here again, and that's the exponent in the Pascal equation. In this case, for KT7 for KT 2.5, it's 7.1. So we use that, and we use that ratio, and 68 the fatigue limit, 90 the applied stress. Well, at home, if you have the Pascal equation and you do some rewriting, you can reproduce this formula. At the end, you will find a life of 130,000 cycles, so 1.37 to the power times 10 to the power 5. And that would be the very simple approach to find the life.
Yeah, for my full understanding, you're basically in this so let's say the fatigue specialist, the specimen was used to get to do tests, and that provided the SN curve. So that is all, directly resulting from experimental data. And what you're doing here is you basically just read out the point in the graph, but then the equation is like a fit on the slope part of the graph.
Yeah, that's in a nutshell what you're doing. And of course, provided that you have the SN curve available for the KTs 2.5, but even if you don't have it, you might be able to establish it or find it from some data. But in a nutshell, you just read the life from the SN curve.
Yeah. All right, perfect. Yeah.
Okay, let's see how or what is often done in let's say, the finite element world. Okay. What are you doing with finite elements? You model your construction, in this case, the strip with the open hole, very simple component. And if you mesh your model fine enough, you will find that you have a peak stress at the edge of the hole 2.5 times the 90 MPa, and that is then 225 megapascal. Well, basically you have a local stress there, and that local stress doesn't see any additional stress concentration factor anymore. So your first approach might be, okay, I have a local stress, no notches, whatever, look just at the local stress, and I will take the SN curve for KT1. In this case, that is then the blue curve here. And then we have a higher fatigue limit, but also a higher applied load, 225 MPa, somewhere here. Well, it's logarithmic scale, so it's somewhere here. You calculate it again with the formula. You have a different slope here, so a different exponent. And basically you find a somewhat different answer. In the previous calculation, where we just used the KT2.5 curve, we find something of 137,000 cycles, and here only 752 cycles. So using this SN curve for KT1, based on the fact that we have local stresses, which are not further affected by stress concentrations, you find a different answer, and that's somewhat strange.
Yeah. All right, let's dive in. What went wrong?
What went wrong? What you can see already here is that you use a different exponent. So we dive a bit further in the question, what went wrong, and what I've done as a fatigue engineer, I just took the SN curve for the appropriate KT value and read the fatigue life from it. The finite element engineer based his analysis or her analysis on local stresses and assumed that an SN curve of KT1 could be representative for those local stresses. As you can see, slopes are already different. So in this case, we ended up here, and in the other case, we ended up here. We have to look to what the actual meaning is of the KT value, so the stress concentration factor. It's a geometrical factor. You already asked me, how do you determine the KT? Well, it's depending on the geometry, and the geometry only, in fact. And it does only mean that the peak stresses, so the local stresses, are a factor KT, in this case 2.5, higher than the nominal stresses. So if you want to read your fatigue life from the SN curve, you have to maintain this factor KT all over the diagram. So here it's a factor 2.5, but if you want to use this curve here in this part, you still need this factor 2.5 here as well to get the right answer. And that's basically what went wrong.
And why can't you use KT1 SN curves with local stresses? I mean, you do you estimate the value of the peak stress in order
Yep.
to know, the value without the amplification, basically.
Yeah. Now, well, basically, if you do it, you assume that only the KT, so only the local stresses, are decisive for the fatigue behavior. But it's not only the local stresses itself, but also the stress gradient. If you have a KT is 1, you have a homogeneous stress distribution. But if you have KT is 2.5, you have a rather steep gradient at a notch, and that also affects the fatigue behavior. And that means basically you have to look to the actual SN curve. We have a look to the next slide. We have again this diagram, SN diagram, showing the SN curve for KT is 2.5 or for KT is 1, and this is based on nominal stresses. You can also translate this diagram to SN curves for local stresses. Obviously the KT is 1 curve remains the same because you multiply with 1. And the SN curve for KT is 2.5 is multiplied with 2.5. And that gives you this orange curve. There are some effects that also causes that the fatigue limit is not exactly the same, but for this discussion we leave it out. So we assume that the fatigue limit is then the same, and that we had a factor 2.5 between the fatigue limits. But yeah, you see that you get for local stresses different SN curves for the different KTs. And that's not only for KTs 1 different from KTs 2.5, but for example, if you take KT 1.5 or KT is 4, you get again different SN curves. Basically,
why is that, Johannes? Why does it have different slopes?
Well, that's basically as I mentioned, we have the peak stress at the hole, but if you have different KTs, you have a different stress distribution through the net section, and the steeper the curve, the better in fact it is for fatigue. So the steeper the stress gradient at the hole, also the steeper this curve here will be. There are some other effects as well, but that's one of the main effects.
Yeah, and I mean that has to do with like the ductile nature, I guess, of steel to some degree, right?
Yeah, that's for a large part what plays a role. Yeah. But yeah.
All right. Yeah. Thanks.
Okay. So to summarize what went wrong, a fatigue specialist would like to take, as mentioned here, experimental data directly. So basically uses a SN curve for the KT and gives or achieves a fatigue life of 137,000 cycles. The FEA engineer, if he really takes the KT1 curve, gets a very short life compared to what the fatigue specialist would translate. And basically, he uses the local stresses, but uses then an incorrect curve, the wrong slope, wrong K value it means. And that's because he only takes into account the KT value and other parameters that affects the SN curve. The stress gradient at the notch, another one, by the way, is the stress ratio of your cycle, also has an effect on the slope. And those are neglected. So he assumes, or might assume, it's not always done that way by an FE engineer, but he might assume that, an SN curve for KT1 is representative for local stresses. And that's wrong.
Yeah.
So, how can we...
how to deal with this,
Exactly. Well, what you see quite often in handbooks, in guidelines, in calculation codes, is that those codes describe a certain slope of the SN curve. And that slope is then represented by the exponent of the Pascal equation, and they use then a value for that exponent of k is 5. That's already much better than using an SN curve for kt is 1. So if you do that, for example, you have the peak stress of 225 again, the local stress. If we have an exact fatigue limit, then also corrected for what we call notch sensitivity, but we are not going to dive in that part further in this discussion. But if you correct that, you would have a fatigue limit for the KTS1 of 170 MPa, so that's somewhat higher than the 155 we had before. And we use then the K is 5. Well, you can have another calculation, and then you would end up in this case with, 246,000 cycles. That's much better than this 750 cycles, but it's still a factor 2 of the result you would have with the KT 2.5 SN curve. A big improvement, but still a factor 2 from the actual result. The result as it should be.
If I may ask, where does k is equals 5 come from?
That's a rough estimate done by those people making the equations, making the codes, making the handbooks. It's easy to use. Always use k is 5, and you don't have to think to bother about it much further. But it's I think a factor 2 away from the actual result. In this case, it's even unconservative. You calculate too long life. I wouldn't feel comfortable with it. So, on the other hand, if you do have the SN data where they use the K is 5 in the handbooks and guidelines, they are often quite, they use the conservative side. So the probability of failure is only 2.5% or whatever. You apply some additional safety factors, but those safety factors are not really meant to cover this mistake, this error or incorrectness or whatever you want to call it. So I'm still not very happy with it.
All right. How would you go about this? Find a different K value, I guess.
If you want to use indeed the local stresses, that would be an option. But the most logical one would be using the SN curve for KT's 2.5. In this example, that's quite easy. On the other hand, if you have very complex geometry, a very complex structure, where you cannot easily calculate what the KT is and not very easily define what your nominal stress level is, then you will end up with a calculation with local stresses. And then you have to think a bit more about what K value, what exponent you use. What I've done some time ago is making a short overview of how those K values vary with different situations. For example, I made the calculations, or not really calculations, it's just estimations, where I have a certain fatigue limit and a certain, let's say, the upper limit, strength of the material, different KT values, stress concentration that's not very severe, that's moderate, and that's severe. Different loading conditions, so R is equal to 0, what we used in the in this example, but you can do it also for R equal -1. Basically, then you have a cycle in tension and compression. Well, then you see that you get really different K values, so different slopes of your SN curve, and it also differs per material. For aluminum, it's different than it is for steel. And in this case, it varies between 3.6 in this table to over 15, and that's really a flat curve. So using K is cutting the edge is a bit too much, I would say.
But these K values are from experimental data fits again, right?
Not really experimental data. It's from a rough estimate of the fatigue limit compared to the tensile stress of the material, and then constructing an SN curve. Basically, that's already some kind of an estimation. If you really use SN data, you will see that for the different situations, you get also some scatter in those values. So that makes it even more complicated. The point of it is that you should recognize that those exponents can vary quite a lot depending on the severity of your stress concentration and on your loading conditions and on your material.
Yeah.
And that's a bit overlooked in most of the guidelines and calculation codes.
All right, interesting.
Yeah, certainly. So let's have a summary of what the pitfall is. Basically, a misconception is that you can analyze such a structure using the KTS1 fatigue limit. Yeah, in the worst case, also using the complete KTS1 curve. But even if you take a estimated K of 5, that it will lead to accurate fatigue analysis results. Basically, the FA analysis, so calculating the stresses, that's very accurate. You can do that extremely good with FA analysis. But the next step, and sometimes it's even included in your software package, finite element software package with some add-ons, that you can have a very accurate fatigue analysis with using KS5. That's too optimistic. So the input for your calculation is very accurate, but the fatigue analysis itself is not that accurate at that moment, and you have to be aware of that.
Yeah, interesting. It's always tempting when you're under pressure engineering work, that to use the code values. But this is a very interesting nuance.
Yeah, certainly is. As I mentioned, very often the codes, the probability of failures of those SN curves are very low. It's not often a typical curve, but very low probability of failure. And that makes it that, probability that you really get a problem, of course, a bit lower. But it doesn't mean that you never get those problems.
Yeah, exactly. Yeah.
Okay, some closing thoughts. Well, very clear now should be that peak stresses cannot be used with a KTS1 SN curve. We've seen that you get answers which are way off the exact solution. So always remember KTS1. Yeah, you can use it for nominal stresses if you have a structure without any notches, but not for peak stresses. You should be aware that a local stress can be a combination of, or any combination of nominal stresses and stress concentrations, and each combination has its own SN curve, and those SN curves are different. So that means at the end that the use of KS5 is not always correct and not always conservative even. So you have to be careful with that. So finite element analysis is very good to determine what your KT is, what your peak stresses are, your local stresses are. But the next step is always use a appropriate SN curve.
All right. Interesting. Yeah. Thank you. Thank you very much, Johannes.
You're welcome.
I have to admit that this is definitely a nuance that is interesting to me. Like I've been involved with these things, but I haven't been in a long time. But it shows again, you know, the importance of knowing where the values in the code come from and what assumptions are behind them.
Yeah, it's always good to as you mentioned, what the assumptions are behind it, what the background is of such a code, and sometimes it's good to dig a bit deeper into the matter, and and that's why you're offering courses.
Yeah, exactly.
Yeah.
All right, let's wrap things up, Johannes. Let me just switch the screen. One second. All right. Let me just wrap things up by saying, you know, if you're watching this video and you feel that this is definitely touching upon, you know, the things that you do for work, for projects, for your interest, definitely head over to EngineeringTrainer.com and check out the courses that Johannes provides. I mean, this is like, let's say, half an hour of discussion. And the course has 13 hours of detailed fatigue training, or check out any of the upcoming virtual instructor-led training that might be scheduled. Looking forward to having you on board. Obviously, if you have any questions, you know, connect with me on LinkedIn or shoot us a message. I do invite you also to subscribe to the EngineeringTrainer.com LinkedIn company profile and the EngineeringTrainer.com YouTube channel. If you want to stay up to date about what's coming, new releases, new content, make sure to do so. Having said this, Johannes, thanks for making the time and elaborating on this topic.
You're welcome. Very nice to join you in this interview, and hopefully we can help a lot of people with it.
Exactly. All right. Have a great day, and thanks for watching.
Thank you.